In the previous screencast, we proved the two fundamental theorems of calculus which link differentiation to integration. Now we're going to apply them using the definite integral developed in the fundamental theorems. The fundamental theorem of calculus states that if we want to find the definite integral from a to b of f of x dx, where f of x dx represents the derivative of a function, that result is going to be the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a. And to understand where that comes from, you've got to go back to part 1 of this screencast. That's the fundamental theorem of calculus. So we're going to use another important notation to denote this f of b minus f of a, and that is capital F of x with this bracket from a to b, meaning we're going to evaluate the antiderivative at b minus the antiderivative of a. It's just a concise way to write this out. So let's get to an example. Let's say we're trying to evaluate the definite integral from 1 to 5 of the function x squared plus 1 dx. So we're going to integrate this function, and if you'll recall from our rules of integration, we can split this up using the sum and difference rule, and this becomes the integral from 1 to 5x squared plus the integral from 1 to 5 of 1, which when we write it out in our new notation is 1/3 x to the third plus x, evaluated from 1 to 5. So this part right here is an important new notation that denotes we've taken the antiderivative and we're now going to evaluate it for f of b, which is 5 in this case, minus f of 1. So we're going to go f antiderivative at 5 minus the antiderivative at 1, which is f of b minus f of a. And when we evaluate the antiderivative at 5, we get 5 to the third over 3 plus 5. Antiderivative at 1, we get 1 to the third over 3 plus 1. So this is f of b minus f of a, which gives us 46.6 repeating minus 1.3 repeating, or 45.3 repeating. So we've now found the exact value of the area under the curve from 1 to 5 of x squared plus 1. So here's a graphical view of what that looks like. Here's the function f of x equals x squared plus 1, and we're finding the area, the exact area, by the way, between 1 and 5 underneath that curve. So let's talk about the mean value theorem for integration, which is going to actually give us the average value over a changing function like this f of x. And it requires, of course, that the function be continuous over an interval from a to b. And if that's true, there must be a point, we'll call it x equals c, somewhere on that interval where that's the actual mean value over the interval. If the area under the entire region is f of b minus f of a, then there's got to be a point c that when we found f of c, it would be exactly the average. And we could find f of c, since this has to be true, by dividing both sides by b minus a. And that gives us the average value of the function being f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Now let's prove that. Okay, we know the fundamental theorem of calculus tells us that the integral from a to b of f of x dx is equal to antiderivative at b minus the antiderivative at a. Well, from the mean value theorem of differentiation, there must be a point along that interval where the instantaneous rate of change equals the average rate of change. In this case, that's going to give us the average value over the interval. And if you'll recall, we can get average rate of change by y2 minus y1 over x2 minus x1 over the entire interval, which in this case is capital F of b minus capital F of a over b minus a. That's going to give us, and another way to write that is f prime of c times b minus a equals f of b minus f of a, multiplying both sides by b minus a. And by substitution, that means since capital F prime of c is the function itself, times b minus a, we know from the fundamental theorem of calculus that f of b minus f of a is the integral, the definite integral from a to b of f of x dx. So we can find that average value f of c by dividing both sides by b minus a, which gives us this formula here. The average value is equal to 1 over b minus a, 1 over the endpoint, the difference between the endpoints, times the integral over that interval from a to b. So let's apply this. Let's say we want to find the average value of the function f of x equals the square root of x over the domain from x equals 1 to x equals 5. So we're finding what's the average value. So for this function, the average value is going to be 1 over 5 minus 1 times the integral from 1 to 5 of the square root of x dx. So if we evaluate that, f of c is then 1 over 4 times, and of course if we rewrite x, the square root of x as x to the 1/2, the integral of x to the 1/2 is x to the 3/2 over 3/2. So the 3/2 in the denominator becomes 2/3 times a fourth, which simplifies to 1/6 x to the 3/2 evaluated from 1 to 5. So f of b minus f of a gives us 1/6 times 5 to the 3/2 f of b minus 1 to the 3/2 f of a. And so 1/6 times 5 to the 3/2 minus 1 to the 3/2 is equal to approximately 1.697. So 1.697 is the average value over the function square root of x between 1 and 5. And this average value occurs at an x value of 2.879. So the average value along this entire interval is 1.697, which is an incredibly useful idea. If we have things that are constantly changing, like we do in our world, to be able to find the average over a period of time is very useful in so many different ways. Now, the limits of integration need not be constants either. Let's say you were asked to evaluate the integral of sine t dt from 0 to several points. Let's say x equals pi over 2 and pi. Rather than doing the integration each time, and if you had to do this many times, you definitely want to do it a different way. Rather than evaluate the integral many times, let the upper bound be x. So the integral from 0 to x of sine t dt is equal to the negative cosine of t evaluated from 0 to x, where 0 is a and b is x. And that's f of b minus f of a, so it's negative cosine of x, substituting an x for t, minus negative cosine of 0, f of b minus f of a, which in turn is equal to negative cosine of x plus 1, because the cosine of 0 is 1, negative of negative 1 becomes positive 1. So now I've got the evaluation of this integral, and I can just substitute the values of x to find the two values that I need. And f of pi over 2, the area from 0 to pi over 2 would be negative the cosine of pi over 2 plus 1, which is 0 plus 1, or 1. So the area between 0 and pi over 2 of this function is equal to 1. In a similar way, the integral from 0 to pi of sine t dt is equal to f of pi, so that's negative the cosine of pi plus 1, which is the negative of negative 1, or 1, plus 1, which is 2. So the area from 0 to pi is actually equal to 2. So we've taken the fundamental theorems of calculus and applied them to find definite integrals and also the average values of functions.